Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 5, Lesson 6 on more work with e and the natural logarithm. Now I will say before you even start with this lesson, two things. You absolutely have to have seen our introductory lesson on the number e and the natural logarithm. This is not the place you want to start with those two topics. You also want to make sure that you have a graphing calculator on you today because we're definitely going to be using that a bit. All right, that being said, let's jump right into it. Here we go. An important inverse relationship. The number e is used extensively as a base in exponential functions because of certain properties that it has that are best understood in calculus. We want to work with it and its inverse, the natural logarithm, more in this lesson. So let's take a look at exercise number 1. Given the exponential function y equals 5 times e to the 7x minus 10, find a formula in terms of the natural logarithm for its inverse function. Show the steps you take in solving for your answer. All right, well, a few lessons ago we looked at how to find the inverse of an exponential function. The only difference then was that we didn't have the number e as a base. Here we do. So, pause the video now and see if you can figure out what the inverse of this particular exponential function is. All right, here we go. Well, let's review. Step 1, whenever you're looking for the inverse equation, we're going to take our function and we're going to simply switch the roles of x and y. So the first thing I'm going to do is make a y into an x and make an x into a y. Okay, so now that's what I want to solve. Now before we solve that particular equation for y, let's just talk about it. So we look at this, don't worry about the x, right? We look at this side and we say, well, what's happened to y? We've multiplied it by 7, we've exponentiated it with a base of e, we've multiplied by 5, and we've subtracted 10. To undo that, we're going to add 10, we're going to divide by 5, we're going to take a logarithm with a base of e, i.e. the natural logarithm, and then we're going to divide all of it by the number 7. All right, let's do it. So, first things first, let's add 10 to both sides. All right, we'll have x plus 10 is 5e to the 7y. We'll divide both sides by 5. We'll get e to the 7y is equal to x plus 10 divided by 5. There's no real need to distribute that division at this point, so I'm not going to. I'll take the natural logarithm of that entire quantity. Those two will cancel, and we'll get 7y is equal to the natural log of x plus 10 divided by 5. And then we'll divide all of this by 7. So y will be equal to the natural logarithm of x plus 10 divided by 5, all divided by 7. Very likely, this would be written, if it were in a multiple choice setting, as 1/7 times the natural logarithm of x plus 10, all divided by 5. Now, don't get me wrong, either one of these would be a particularly good answer for the inverse equation, but you can imagine in a multiple choice scenario, they might put this answer down instead of this answer simply because this one takes up less space. All right, hopefully you're already comfortable with the idea that dividing a quantity by 7 is the same as multiplying it by 1/7. If not, well, maybe get used to it. I don't know. All right, let's keep going. Here we go. The graph of the natural log. The graph of the natural logarithm follows the same pattern as that of all increasing logarithms, right? Now we looked in lesson 2 of this unit at the graphs of logarithms, okay? And we kind of noted that any logarithm whose base is greater than 1 is an increasing logarithm and kind of all looks the same. So let's take a look at exercise number 2. Given the function f of x equals the natural logarithm of the quantity x minus 3, do the following. Letter A, use your graphing calculator to help sketch a graph of the function. All right, well, why don't you go ahead and put this thing into your graphing calculator, pay attention to the window that I've given you, and do the best sketch that you can that's possible. All right, well, let's do it. Easy enough. We haven't graphed the natural logarithm yet, so I think I'm going to add a page. When I do this, put in the natural logarithm of x minus 3, and we'll hit enter. All right, we don't see much there. I don't know that that actually worked. Let me try that again. There it is. Oh, I think I just got the natural logarithm of -3, which is very different. There it is. All right, let me make sure that it's got the same window as this one does. That's a window that goes from -2 to 10 along the x-axis, and then -5 to 5 along the y-axis. There it is, right? So there's our function. Kind of looks a little bit like this. Okay. And I know that it goes through an x-intercept of 4, but as long as you've got that pretty close, that's fine. Let's take a look at letter B. What asymptote does this function have? State its equation and draw it on the graph as a dashed line. All right, well, keep in mind, right, that all exponential functions, all logarithmic functions that look like this, the log base b of x, have a vertical asymptote of the y-axis. Now, that includes y equals log base e of x, but this is one that has been shifted by 3 units to the right. So this thing has a vertical asymptote at x equals 3. All right, so if we put in a vertical line at x equals 3, remember asymptotes we draw in as dashed lines, there is our vertical asymptote. Let's take a look at letter C. If g of x equals 0.5x squared minus 2.5x, then determine all solutions to the equation f of x equals g of x to the nearest hundredth. All right, so in other words, what we're trying to do is solve the equation ln of x minus 3 is equal to 0.5 x squared minus 2.5x. The only way to solve this equation is to do it graphically. Pause the video now and see if you can find the solutions to this equation, and there will be 2, to the nearest hundredth. All right, well, we want to graph both sides of the equation and find their intersections. Luckily, we've already got the left-hand side graphed, right? So this one I put in f1 of x. This one I'll put into f2 of x. So let's do that. All right, menu, graph entry edit, function, f2 of x. That's going to be, don't want that, 0.5x squared minus 2.5x. We hit enter. Beautiful, right? What's really great about this is that we can see an intersection point here and we can see an intersection point there. We just have to use our calculator to find those 2 intersection points. I think we'll probably just do one of them together. Just want to avoid doing that. So I'm going to go menu, analyze graph, intersection. Maybe put it right about there, enter, there, enter. Right, we've got this intersection at 3.051 comma negative 2.973. We'd want to label that on our graph, but ultimately, right, to the nearest 10th, 100th, what do we want? To the nearest 100th, all right, there we go. To the nearest 100th, one of our answers is going to be 3.05. And if you find the other intersection point, it's at 5.32. So we would, let's go back in, full screen. Maybe I'll go red just like the calculator. We would get some kind of graph that looked like this. This intersection point, which would be at 3.05 comma negative 2.97, and this intersection point, which would be at 5.32 comma 0.84. And then that would give us our 2 answers, which are x equals 3.05 and x equals 5.32. All right. To save a little bit of time, I'm going to forego doing some things I really should be doing, like labeling both of these curves with their equations. That's very important. Anytime you give a graphical solution, you want to make sure both curves are labeled with their equations, i.e. f1 of x is equal to this, f2 of x is equal to that. Make sure you've labeled your intersection points, etc., and then your answers are simply those x coordinates. All right, let's keep going. Always good to just review how to use a graph to solve an equation. Creating exponential models. Many growth and decay models are placed in a form that has e as its base. Sometimes we need to solve for a particular parameter in these models. Let's take a look at that in exercise number 3. A population of mice can be modeled using the function p of t equals p sub 0 e to the kt, where p sub 0 is the initial population of mice and t is time in years. A colony starts with 20 mice. After 5 years, the population has grown to 30 mice. Use the information given in letter A, use the information given to find the value of p sub 0 and of k. Round k to the nearest thousandth. Okay, great. So what I'd like you to do is see if you can figure out the values of p sub 0 and k. P sub 0, or p ought, should be very, very simple. But then, once you have that, see if you can use the fact that after 5 years there are 30 mice to figure out the value of k. Pause the video and play around with this a little bit. Well, we're literally told that p sub 0 is the initial number of mice, so that's 20, right? Simple enough. And let me go back to blue. All right, so p sub 0, which is equal to p of 0, is equal to 20. And that means that p of t is equal to 20 e to the kt. All right, now, I know that after 5 years, the population is equal to 30. So what I'm now going to do is I'm going to put 30 in for p, and I'm going to put in 5 for t. And that's going to leave me only a k in my answer. Now I have to solve for k. To do that, I'm going to divide both sides by 20. All right, so I'm going to get e to the 5k is equal to 30 divided by 20. And I think for once, in a very long time, I'm going to simplify that to 1.5. Now what I'm going to do is take the natural logarithm of both sides. That makes sense since I have an exponential with a base of e. So I'll have ln of e to the 5k. Those will cancel. That'll give me 5k is equal to ln of 1.5. And now I can divide ln of 1.5 by 5. And that will then give me the value of k. Continue to extend the page. K will be, what is it? That is just the wrong sheet. K is going to be 0.081. All right, and now let's write down our model. P of t is equal to 20 e to the 0.081 t. All right, we want to get our nice exponential model there. Okay, and again, it's a natural use for the natural logarithm, right? We're missing this parameter in our model, okay, possibly called a growth factor, up there. And what we can figure it out because we've got this point 5 comma 30 that lies on our function, so we can just substitute it in. We use our natural logarithm to solve for k, and then that allows us to flesh out our final model. Now, let's take a look at letter B. Place the model in the form p of t equals p sub 0 times b to the t. Round b to the nearest thousandth. What does the value of b tell you? All right, it's been a little while since we've done this. Let's write down our model again. P of t is 20 e to the 0.08, what was it, 081 t. All right? But we don't want it written in this form. What we'd like to do is we'd like to rewrite it as p sub 0 equals some number raised to the t power. So we've seen this trick before. We're going to run the product rule for exponents backwards, if you will. In other words, I can rewrite this as the following. P of t is equal to 20 times e to the 0.081 all raised to the t, right? Because when we have something raised to an exponent raised to another exponent, we multiply their exponents. But we can use that in reverse by saying, well, if we've got the product of two exponents, I can rewrite this by just having e to the one exponent, then raised to the t. And now, we just have to use our calculators because clearly b is equal to e to the 0.081, and that's going to allow us to figure out what b is. So, pause the video now, use your calculator to figure out what e to the 0.081 is. That's the value of your b. It says round it to the nearest thousandth. All right, so figure out what that is, and then see if you can interpret what the value of b tells you about the growth rate of these mice. All right, well, if we put that in our calculator, and I'm not going to take the time to go through that because we've put plenty of those in, P of t will be 20 times 1.084 to the t. So e to the 0.081 is 1.084. And now how do we interpret that? Well, keep in mind, anytime that we've got an exponential model written in the form a times b to the t, we should be able to look at this value and now say, oh, that's 1 plus 0.084, and therefore the mice population is growing at a rate of 8.4% per year, right? So as long as we've got our model written as something times b to the t, we should be able to interpret it as a percentage growth rate per unit of that time. So we're growing at a rate of 8.4% per year. All right, let's keep going. Let's talk about compound interest, right? So we looked at compound interest in our last unit with exponential functions. Now the number e takes an important role when it comes to compound interest, all right? And let's see how that plays out in exercise number 4. A $500 investment is made at 5% nominal yearly interest. In each case below, write a function for the amount of savings, a of t, after t years for n compounds per year in the form a of t equals p times 1 plus r divided by n to the nt. Then write the model in a of t equals p times b to the t form, round b to 5 decimal place accuracy, which probably seems a little silly, but just trust me on this. All right, let's do the first one together. Now I've given you the compound interest formula, a formula that we derived in the last unit, and I hope makes sense to you, so we're not going to kind of go through that so much. But, right, so letter A, what's our model look like? We put in $500, right? We've got quarterly compounding, so we're going to have 1 plus 0.05 divided by 4, all raised to the 4t. All right, so that's our normal model, and I apologize, it should be all of this raised to the 4t, not just sort of this quantity, but I ran into a wall. I have to write smaller. All right, now, we want to do the same kind of manipulation that we did in the last unit, and in fact, in the last problem, okay? I want to rewrite this in terms of b to the t. So to do that, what I'd like to do is I just want to take this and rewrite it like this to the 4th, all to the t. All right, so I'm just separating that product exponent and bringing the 4 inside. And now I just want to take my calculator and figure out what that is. So, and we're going to figure it out to 5 decimal place accuracy, which, yes, I realize it's a lot, but whatever. All right, so I've got 1 plus, I'm going to use the fraction 0.05 divided by 4. Whoops, that's not really what I wanted. Raised to the 4th. Now the great thing is we're going to be kind of doing this calculation again and again. There we go. And we have 1.509, etc., right? And to 5 decimal places, that's 1.05094. 1.505094. A lot of it, all right? So let's go back to here. A of t is 500 times 1.05095 to the t. I just want to make sure 1, 2, 3, 4, 5. Let's see, 1, 2, 3. Yep, that's right. 1.05095 because the 5 bumps the 4 up to a 5. That was a little confusing, and now I'm not going to have enough room again. Okay. Now, the only difference for part B, C, and D is the fact in part B, you're going to have a 12 down here and a 12 up there. In part C, you're going to have a 365 down there and a 365 up there. And in part D, strangely enough, you're going to have a 10,000 down here and 10,000 up here, which is kind of cool because you don't really have to change much in each case. Now, as a side note, right, this would be compounding 4 times a year, quarterly compounding. This would be compounding 12 times a year, so monthly compounding. This would be compounding 365 times a year, so daily compounding. And this one would be compounding 10,000 times a year, which doesn't even have a word for it, all right? It's definitely more than once per day. You know, it's probably even more than once per hour. Anyway, what I'd like you to do is do the same thing that I've done here for each one of these. Hopefully, you'll have enough space. All right, pause the video now and see what you can do. Okay, I don't even know how I'm gonna fit this. All right, so in this case, I'm going to have A equals 500 times 1 plus 0.05 over 12, all to the 12t. Okay, that's our normal, or our model written in its normal sense. If I bring the 12 inside, like I did the 4 before, and then I do that calculation, which I'm going to skip just to try to give myself a little bit more room, and I'm never going to have enough room to write the entire base there, but the base ends up being 1.05116 raised to the t. Now, just before we move on, I'll put a little dot there. Right, just like in our last exercise, we can look at these numbers and we can interpret them in terms of an effective rate. Right, so when we compounded that 5% quarterly, we were actually getting 5.095% interest, 5.095. When we compounded it monthly, we were getting a little bit more. We were getting 5.116%. And I want to make sure that looks like a 5 and not a 6. All right, so a little bit better, right? 5.095 versus 5.116. Now let's take a look at daily, right? For daily, the model would be 500 times 1 plus 0.05 divided by 365 to the 365t. And again, if we do that manipulation where we bring the 365 in and leave the t outside, we'll get A equals 500 times, and I'm going to put the multiplier down here, 1.05127 raised to the t. So again, just to review what that tells us, right here we're getting an effective 5.116% rate. Here, 5.127% rate. So just a little bit more. And then if we compound 10,000 times in a year, right, which is more than once per day. Again, I'd have to run the numbers to see if it's, once per hour or once per minute or whatnot. But again, the actual model, 500 times 1 plus 0.05 divided by 10,000 to the 10,000t. All right, and then when we actually did that calculation, it would be 1.05127 again. Now, rounded to the nearest 5 decimal places, these two gave us the same thing. They are certainly not the same number, and really quickly, let me just kind of bring the calculator out. Let's just do that, those two calculations really quick. So if I grab this one and I literally just go up and change this to 365 and go in the denominator and change that to 365 and hit enter, there's our 0.05127. But now if I go up and I grab it and I change this to 10, 1, 2, 3, 10,000, and then I change this. No, that's not what I wanted. Oh well. Best of intentions. Change this to 10,000, 10,000. Wait, to the 10,000, right? Both of them are rounding to the same thing, 5 decimal places, but they are a little bit different, right? They round to exactly the same thing though, 5 decimal places. Now I want to leave those calculations up there because let's look at the last piece of this problem. Well, actually it's the next problem. Exercise number 5. Evaluate e to the 0.05 accurate to 5 decimal places. What do you notice? All right, go for it. Take your calculator out and just raise e to the 0.05 and see what you get. Now notice this is e to the 0.05. This is not e to the 1.05, it's e to the 0.05. And if we do that, let's just do it right here, right now, e to the 0.05, look at that. E to the 0.05 is almost exactly this number. All right, now remember, every one of those numbers was giving us just a little bit more interest, right? A little bit higher of an effective rate, but we were compounding at a faster and faster pace, right? We went from 4 times a year to 12 times a year to 365 times a year to 10,000 times a year. So what does the e represent? Given that that number and that number are nearly identical, e represents what we get if we're compounding continuously. Every moment, not every second, not every half second, every moment of time we're compounding. Literally, if we could put an infinity down here and an infinity up here, that's what would give us this number. And of course, that number is just barely bigger than this one and barely bigger than that one. So what am I going to say? I'm going to say e to the 0.05, accurate to 5 decimal places, is 1.05127. What do you notice? It's the same base. Well, maybe I should put almost. And maybe I should put almost there. Almost the same base as exercise number 4D. It certainly is the same base out to 5 decimal points, but it is a little bit bigger. And that leads us to the final topic with e and the natural log, called continuous compounding. Some types of compound interest occur continuously. When continuous compounding occurs, the number e is used to calculate the worth of the account. So this is one of the most famous formulas in all of finance, called the continuous compound interest formula. Let's take a look at it. When an account earns a nominal yearly rate of r that is compounded continuously, the amount it is worth t years after the principal p was invested is given by a of t equals p times e to the r raised to the t, or simply p times e to the r times t. Sometimes this formula is literally in finance classes referred to as the PERT formula. Literally, the PERT formula, which almost sounds like Kirk. Coincidence? Yes, absolutely. The PERT formula. And the real thing is, it's a direct extension of the normal continuous compounding formula, even though it doesn't look almost at all like it. It's simply that when n goes to infinity, when you're compounding an infinite number of times in a given year, right, then the base of that function becomes e to the r. All right, but then because e to the r is then raised to the t, it just becomes p times e to the rt. Let's take a look at that in exercise number 6. A person invests $350 in a bank account that promises a nominal yearly rate of 2.5% continuously compounded. Letter A, write an equation for the amount this investment is worth after t years. All right. Now this is really key because it's a point of confusion for a number of students, right? So the PERT formula, P is equal to, A is equal to P e to the RT. The thing that can really get to students is that the R value. So the R value here is 0.025. It is not 1 plus 0.025. So in all other cases, we always had this 1 plus R divided by N. That goes out the window when we're talking about continuous compounding. Here, literally, it's E raised to the 0.025 times T. Now, what's the original P? The principal is how much we invest at the beginning, which is $350. So the amount is going to be $350 times E to the 0.025 T. If you put a 1 in front of that 0.025, if you have 1.025 to the T, oh man, you're getting 102.5% interest, which is awesome, but no bank is going to give you that. It just isn't going to happen. All right, let's take a look at B. How much would the investment be worth after 20 years? Well, that should be pretty easy. You just need to evaluate this function when t is equal to 20. Why don't you go ahead and do that now? Take a couple minutes or a couple seconds to do that. All right, well, so we're just looking for a of 20. All right, and that would be 350 times e to the 0.025 times 20. You should be able to put all of that into your calculator all at once, no intermediate steps. And what you will find is a very messy number, but if you round it to the nearest hundredth, which is appropriate with money, we would get $577.05. And by the way, that's the best you're going to ever do, right, at 2.5% nominal interest. You can't compound any more quickly than continuously. So if we looked at this, compounding once a year, it would be less. Quarterly, it would be a little bit more than once per year. Then monthly, daily, etc. This is as good as it's going to get. It's what's called the limiting case. All right, let's take a look at letter C. Algebraically determine the time it will take for the investment to reach $500, round to the nearest tenth of a year. Awesome. Well, let's write down the equation that we're going to solve, right? And the equation we want to solve is 350 e to the 0.025t is equal to 500. All right. Now I'd like you to go ahead and solve that equation using a natural logarithm. Pause the video now and go ahead and do that. And again, I really encourage you when solving an exponential equation to always walk through the steps in your head before you write anything down. We have e raised to the 0.025 times t multiplied by 350. First thing that we're going to do is divide by 350 on both sides. Then we'll take the natural logarithm to get rid of the base of e, and then we'll divide by 0.025. In fact, for some of you, just walking through that, you might be able to write down t equals and write down an expression for it. But let's go through the equation solving steps. Okay, we'll divide by 350 on both sides. 500 divided by 350 might simplify nicely, or it might not. Since it's not obvious to me either way, I'm going to leave it the way it is right now. Right. We'll take the natural logarithm of both sides. That will then cancel out the exponentiation with a base of e. So we'll get 0.025 is equal to the natural log of 500 divided by 350. And now we just have to divide by 0.025 on both sides. We can put that entire quantity into our calculator just like that. And what we will find is to the nearest tenth of a year, it's going to take 14.3 years. A lot of banks and other financial instruments use continuous compounding because unlike other types of compounding, which basically like consider quarterly compounding. Quarterly compounding, your money literally sits in the bank account doing nothing for the first quarter of the year. At the end of that quarter, you multiply what's in there by your percentage rate divided by 4, and it goes up. Then it sits in there for a quarter of the year doing nothing, and then at the end of that quarter, you multiply it by, your percentage rate divided by 4, and you bump it up, right? But with continuous compounding, you don't have to worry about that at all because it's always growing. It literally is a continuous curve. There is no flat jump, flat jump, flat jump, which is in theory what all other types of compounding actually are when it comes to bank accounts that have different types of compounding. Anyway, that was a lot of use of the word compounding. Letter D. What is the effective annual rate for this investment? Round to the nearest hundredth of a percent. All right, so the nominal rate is 2.5%. But what is the effective rate to the nearest hundredth of a percent? Pause the video now and see if you can figure that out. Well, remember, we can always see that rate by taking something that looks like this and rewriting it like this. And that value of b, right? That value of b is going to tell us what the effective rate is. Granted, it's going to be 1 plus the rate, but then we just have to kind of subtract 1 or look at it or whatever. So in fact, it's e to the r. That's the real key. And I just move that right off. So a of t is going to be 350 times 1.0253 to the t. So our effective rate is 2.53%. And notice, right, even with continuous compounding, our rate is just a bit better than what our nominal rate was. Our nominal rate was 2.5%, our effective rate was 2.53%. Now you might say, well, that's not much of a difference. I'll just take it, compounded, once per year. Except remember, again, if it's compounding once per year, number one, it's not doing anything until the end of the year, then it goes up. And number two, yeah, the difference between these two is not very much if you're investing $350 or $200 or something like that. On the other hand, if I take $10,000 or $50,000, if I take, some money I've made and I'm putting it into a retirement account and it's a large amount of money, then that extra 0.03%, that's going to make a difference, especially over time. All right, let's wrap this up. So what we saw today was more work with e and the natural logarithm. And we saw things like, what does the graph of the natural logarithm look like? And the answer to that is, well, like basically any other increasing logarithm, it's just got a base of e, so it can be shifted, might have a different vertical asymptote. We also found how to find the inverse equation for an equation that involves e raised to a variable power. All right, but most importantly, what we saw was what's known as continuous compounding, the PERT formula, i.e. when we're told that we're compounding continuously, as opposed to once a year, 4 times a year, 12 times a year, etc., we have to calculate the amount it's worth by p, the principal, times e raised to the r, which is the rate, times t. All right, and that's just simply because as the number of compounds goes to infinity, that whole 1 plus r divided by n raised to the n simply approaches e raised to the r. All right, so e raised to the r becomes your base multiplier in continuous compounding. All right, well, we'll see this just a little bit more as we go through the course. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.